We ended with the law of definite proportions in compounds. We're going to pick up with that quick review and then get into the law of multiple proportions after definite proportions. So we are on page 54-ish with our review. We talked about compounds. And talking about compounds, remember what a compound is? As opposed to, well, let's say, an element versus a compound. Okay? An element is in the form of an atom. Compound is in the form of a molecule. The compounds are made up of elements. So using the analogy of our Duplos, a compound, if you think of each block as being an element, then each piece, the smallest indivisible piece of the element is the atom. The atoms combine together to form a structure, and that structure is a compound. So a compound, this is a molecule. Each one of these individually is an atom. An atom of an element, atoms of elements combine to make molecules of compounds. Okay. We were going through this exercise where an example here on your own 2.5 says that 24 grams of carbon and 8.08 grams of hydrogen combine to form natural gas. And how much carbon and hydrogen would you need to make 128.4 grams of natural gas? Said there were no leftovers, there was no excess. In other words, this was the perfect balanced recipe. And right now we're using by mass, by grams. Later on, we're going to be using grams, but we're going to use grams to get us to the individual pieces, the individual counts when we form our molecules. But for right now, we're just talking about the mass. 24 grams of carbon and 8.08 grams of hydrogen form natural gas. How much does it make? Well, using the law of mass conservation, the amount of natural gas that's made, if there's no leftovers after the reaction, there's no excess. If 24 grams and 8.08 grams are used, then that same total mass must be how much is produced. I haven't made or lost any of the matter. I've just converted it. I've taken the Duplos and I've made a structure out of it. It's the only difference. So all my basic building blocks that were here in the beginning are still there at the end, but they may look different. They may be in a different form. Okay. Since I started with 32.1 grams, I must end with 32.1 grams. I was told that I want to make 128.4 grams. I have a recipe that'll make 32.1 grams. So I need a reaction multiple. I need to make multiple batches, right? In this case, since it's greater than the amount, I need a number higher than 1. If I was asked to make less than a full batch, I would need a number less than 1. And I figure out what that multiple is by taking the amount that I want to make and dividing it by the amount I can make, or the recipe I have. So I have a recipe here that makes 32.1 grams. I was told I want to have 128.4 grams. So how many batches do I have to make? The reaction multiple is how many batches? I have to have 4 batches. Reaction multiple of 4. So I'd go back to my perfect recipe here and multiply everything by 4. So if I have 4 times as much carbon combines with 4 times as much hydrogen, it'll make 4 times as much natural gas. So how much do I want to make divided by how much do I have a recipe to make, and then multiply everything by that number. So 4 times 24 gives me 96. So 96 grams and 32.3 grams combine to form 128.4 grams. This was another example of the same that we did on 2.6. Then we got into the law, or starting today rather, with the law of multiple proportions. The law of multiple proportions says that if 2 elements combined to form different compounds, and this is written on the bottom of page 57 in your book. If 2 elements combine to form different compounds, the ratio of masses of the second element that react with the fixed mass of the first element will be a simple whole number ratio. I understand that might be a little complicated. We'll give you an example to explain what that means. Use the example of forming carbon dioxide and carbon monoxide. Carbon dioxide is formed with 1 carbon and 2 oxygens. And in just a moment, we're going to go through and make sure you understand how to form the chemical symbols, how to understand the chemical symbols. Right now, 1 carbon and 2 oxygens combine to make CO2, carbon dioxide. And when 12 grams of carbon and 32 grams of oxygen combine to make carbon dioxide, they make 44 grams. That should be obvious. 12 and 32 combined is 44. But carbon and oxygen can combine in a different way. This is not an ionic bond, this is a covalent bond. Again, it'll make more sense later. But carbon and oxygen can make different combinations. And another combination they can make is carbon monoxide, where 1 carbon combines with 1 oxygen to form carbon monoxide, as opposed to 1 carbon combines with 2 oxygens to make carbon dioxide. Now what the law of multiple proportions says, if I look at this and I have one of my reactants has the same amount of mass, and the other reactant has a different amount of mass, they're both the same, carbon and oxygen, but if one of them is kept constant and it reacts fully with another quantity of the same that are different, that the ratio of these two are going to be a whole number all the time. In this case, the ratio is 2 to 1. In the first reaction, it took 32 grams of oxygen combined with 12 grams of carbon. In this case, 16 grams of oxygen combined with 12 grams of carbon. And 32 to 16 is 2 to 1. It's a 2 to 1 ratio. It's not going to end up being 1 to 1.5. It's always going to work out to be a whole number ratio. I don't give examples because even in that I said 1 to 1.5. Well, that's the same as 2 to 3. So yeah, it could be that. But it's always going to be a whole number ratio, a whole number multiple. And that'll make more sense in a few minutes as well as we discover how atoms come together to form molecules. Let's give another example. Maybe it'll make it a little clearer. 36 grams of carbon combined with 12 grams of hydrogen to make 48 grams of methane. Again, you see the law of conservation of mass here. 36 and 12 is 48. No matter is destroyed or made, it's converted into some other form. In this case, carbons and hydrogens hook together to form methane. We can also make propane from carbon and hydrogen. Same 2 basic building blocks, but they come together in a different proportion. 36 grams of carbon doesn't react with 12 grams, it only reacts with 8 grams of hydrogen. So 36 grams of carbon and 8 grams of hydrogen makes propane, which is 44 grams of propane. Now as I look at those two, which of the 2 reactants is kept constant? The same amount in both cases. What's the carbon here, right? 36 grams of carbon in both cases. Since those are the same, if I look over here, I have 12 and 8. What's the relationship between those two? It's going to be a whole number relationship, and it's 12 to 8, which reduces down to 3 to 2. Okay? If these are constant, the relationship here is 12 to 8. 12 to 8. And 12 to 8 simplifies to be a 3 to 2 proportion. So if the building blocks that you're using are the same, to create 2 different products, and the quantity of one reactant is kept constant, the masses of the second will be in proportion. Whole number ratio proportions. A gentleman by the name of John Dalton. He lived from 1766 to 1844. And it was Dalton's atomic theory that set the framework for the way we understand much of chemistry. Dalton had 4 basic assumptions. These are in your book on page 59. But the basis of our modern day interpretation of the nature of matter and things is 4 assumptions were, first of all, that all elements are composed of small, indivisible particles called atoms. The term atom had been around for a long time, but Dalton said, okay, I've got this theory of understanding all the stuff that is, and part of this theory of understanding everything that is includes this idea of basic building blocks, the smallest of which I'm going to call an atom, and the smallest of which cannot be broken down any farther. Remember before we talked about decomposition of a molecule, breaking down, breaking down, breaking down until it can't break down any farther? This comes from Dalton saying, hey, the basic building block, the smallest building block of matter for his purposes was going to be the atom. And we come to find out later that the atom actually is made up of things. But for right now, for our understanding of basic chemistry, the atom is the smallest building block. That all atoms of the same element have exactly the same properties. So again, looking at the Duplos, if we look at this as a molecule made up of a lot of different compounds, or a lot of different elements, and I break it down and I say, okay, I have 2 yellow Duplos. These represent 2 atoms of the very same element. Dalton would say, you know what? These 2 atoms behave exactly alike. They're clones of one another. They've got exactly the same chemical properties. They behave, this yellow and this yellow are interchangeable. They're exactly the same. So the atoms of the same element have exactly the same properties. But he went on to say that atoms of different elements have different properties. In a representation, this blue Lego represents an atom of a different element. And whereas these 2 yellows are exactly the same, a yellow and a blue are not the same. There's something about them that's unique to them that causes them to behave differently chemically. So atoms of the same are identical. Atoms of different elements behave differently. And lastly, that compounds are formed when atoms join together. And since they can only join together in simple whole number ratios because you can't divide them. In other words, let's say that I have a structure here that is made up of these 4 Duplos, okay, these four different atoms. A blue, a red, and 2 yellows. They come together to form this molecule. But they always come together in whole number ratios. In other words, it's always going to be 2 to 1 to 1. If I bring another atom into it, I've got something different. And they can never join, like I can't have a half of an atom. I've either got all or nothing. So compounds are formed when atoms join together, and since they are indivisible, they can only join together in simple whole number ratios. In this case, it's 2 to 1 to 1, not 2 to 1 to 1/2. If we assume that Dalton's correct, it helps explain some things that appear to be true. It explained the law of mass conservation. Dalton's theory explained why the mass of the reactants equals the mass of the products, because all we're doing is taking the smallest indivisible pieces and rearranging them from one side of the reaction to the other. So we're adding no blocks, we're taking away no blocks, so it explains the law of mass conservation. It also explained the law of definite proportions. It told us why, when we combine certain things, we get a certain amount. If we double the recipe, we double the product. If we triple the recipe, we triple the product. It explained it in a way that was understandable. It predicted the law of multiple proportions. It predicted this idea that if 2 reactions take place, and you hold one thing constant, and you're reacting with something else, and you get different products, that those different quantities have to be in whole number relationships, or whole number ratios, a 2 to 1, a 3 to 2, or something like that. This idea here about atoms existing. If we accept Dalton's theory, it helps us understand this idea that that atoms exist, because frankly they are too small to observe or to prove. What we're going to be studying here in chemistry this year, especially when we look at the individual atoms, all of our understanding of atoms, the way we represent it, is based upon theory, and we represent models. Nobody has ever seen an atom. Even on the right there, you see an electron microscope. And what that shows right there, I believe it's silicon. But it's showing the electron microscope would tell you that every one of these represents an individual atom together in a structure to form like a block. This is a block of an element. And individual atoms form a structure. You see, it's nice and uniform and consistent that every one of these is an atom of that element. And yet, what we're seeing here from the electron microscope is not the same way that we think of a microscope, where if I look in one end, that I can have a visual image on the other end, you know, by magnification, that I can take something very, very small and make it discernible. I can see it because of that. What an electron microscope does is it measures electronic fields and uses a model to convert fields into an image. So this image doesn't exist except as a model representing what the field looks like. So if the model is wrong, the image is wrong. Does that make sense? If what we think it looks like, somebody had to go in and program the electron microscope to present the information that it senses in a way that we can see, because it's so small that we can't see it. And we can't just simply magnify it. We don't have the ability yet to magnify from that small to the scale that we can see. There are two assumptions that Dalton gives us that are not completely accurate, but for a basic understanding of chemistry, we're going to treat them as being true. Now, the idea is that different elements have different properties. We're fine with that. And that compounds are made when different atoms join together and they form together in whole number ratios. We're fine with that. This idea that all elements are composed of small individual particles called atoms, yes, we do believe that. They're made of small individual particles called atoms. But this idea about them not being divisible, we can split the atom. We can do damage to the smallest indivisible component. At his time, the idea of breaking the atom apart was science fiction. Nobody would ever, we're not quite sure what would happen if we did that. Now that we're post-nuclear age, we understand we can break the atom apart. But for most of our purposes in chemistry, we're going to treat it as if we can't, because that whole chemical reaction, or the whole process of splitting the atom, is a long, involved process. It's technically doable. I'm not concerned that I left you loose in here with some chemicals over there at the lab that you might accidentally split the atom and blow up the county. Okay? That doesn't cross my mind. You might do something stupid and blow yourself up, but not the county. Not by nuclear fission or fusion. So though while it technically, for our purposes, we're going to say they're indivisible, we recognize, but we can split the atom. We can't actually break it up into pieces. And second, that all atoms of the same element have exactly the same properties. They have virtually the same properties. But this was before they understood the idea of isotopes. We'll get into isotopes later, but remember, the isotope is an element that has a different number of neutrons than another element, another atom of the same element. So you could have carbon. You have carbon-12, but you can have carbon-14. The difference between carbon-12 and carbon-14 is the number of neutrons they have, and they're isotopes of one another. Okay? So there are some differences between an atom, and another atom, and a third atom, a fourth atom, a fifth atom of the same element when we start talking about isotopes. But for the vast majority of the properties we're going to talk about, atoms of like behave alike, atoms of different behave differently. All right. Parts of this module are kind of repetitive because we're talking about things before we define them, and then we're defining things after we talk about them. So just bear with me in the way they present this. The idea of an atom versus molecules. What they're representing on this first side of figure 2.5 is there's a bunch of oxygen that they're showing as red and hydrogen that they're showing as yellow. These atoms of, these atoms of hydrogen and of oxygen are in the same place at the same time, but they haven't come together yet to form molecules. They're just a whole bunch of atoms that happen to be in the same place at the same time. Okay? There's a random chaos here. It's a very unstructured relationship. But On the right-hand side, they're showing the same oxygens and the same hydrogens, but those have come together to form water. And when they come together to form these molecules, we're going to find out later that they have a very specific geometry. They look a very particular way, and they're going to relate to one another in a very particular way. You're actually going to have the molecules start orienting towards each other and turning to each other, because one side of the molecule prefers to be with the different side of the opposite molecule. And so as you have these same hydrogens and oxygens that weren't compounds become compounds, and then those compound molecules start relating to one another, it forms a very defined structure. Just like in the last electron microscope picture I showed you, where everything was in nice rows, nice orderly system and setup, that is what happens as we move from atoms to compounds. A structure begins to form. A structure begins to take place, which is completely natural, part of God's design, from the chaos random to the ordered relationship. Not only relating atoms to atoms within the molecule, but relating molecules to molecules within the greater structure. That all begins to take place. So it's unstructured and unordered, and then they become ordered and structured. We've already covered this, that atoms, if a substance has identical atoms, then that is considered to be a sample of an element. Molecules, all the molecules identical, and that's the name we give to the compound. Okay, so how do we name these things? Every element, we mentioned already looking at the periodic table, that every element has a unique name and an abbreviation, that abbreviation called the chemical symbol or just its symbol. Every molecule has a formula, a unique chemical name based on the elements that make it up. So you're going to be able to figure out what makes up the compound by the name that it has. Remember too, just as an aside, that these letters may not make sense in English because the elements are named either after their English or they're named in Latin, which is why some of the abbreviations don't seem to make sense to the English ear. The English ones wouldn't make sense to the Latin-speaking ear. Okay. The letters that are going to be in the molecule's name, its formula, the letters come from the letters of the individual elements, their individual symbols. And you're also going to have subscripts. Those are the lowercase, the numbers that are smaller and set low. Just like you have exponents that are small and high, the subscripts are small and low. They're going to tell you how many of each one of those elements are part of the compound. But here's the important thing you need to remember, that the subscript 1 is never written. It's always implied. Before we had the example, well, let's use the example here of water. 2 hydrogens, and hydrogens have the chemical symbol, or hydrogen has the chemical symbol of H. 2 hydrogens and 1 oxygen, symbol of O, form to produce water. Water is H2O. There's a 2 subscript behind the hydrogen. That 2 tells me that whatever it's subscripting, in this case it's subscripting hydrogen, that 2 hydrogens combine with 1 water. There's no subscript behind the O. The fact that there's no subscript means that it's a 1. If it was anything other than a 1, it would be written there. If it was anything less than a 1, it wouldn't be, the O wouldn't be there, right? Because imagine if every chemical or every molecule had every element and every one of them subscripted with a 0. You'd have to look through the whole list and find where there's something other than 0. Well, they make it easy for you. If it's 0, they don't include it. If it's a 1, they include it with no subscript. If it's greater than 1, they include it with a subscript. So 2 hydrogens combine with 1 oxygen to form H2O. Often refer to this as the Mickey Mouse molecule. We have water, we deal with water all the time in here. Right now they've got this oriented upside down. It's one way of depicting how the molecule looks. Generally it's written the other way, where you've got this big head and 2 ears on it, right? So you got the 2 ears on top. So we say Mickey Mouse. You remember, water looks like Mickey Mouse. Example 2-3. What's the chemical formula for a molecule that contains 1 atom of sodium, 1 atom of nitrogen, and 3 atoms of oxygen? How would I start by figuring out what that chemical symbol looks like? Remember, what we're covering here today will be on the quiz tomorrow. So, sodium is Na, okay? Well, we know it would have Na, right? So it would have an Na. What else would it have? Nitrogen, which chemical symbol is an N. So you've got an Na, 1 Na, 1 N, and O, so 3 O's. So, right, 1 sodium, 1 nitrogen, 3 oxygens. For right now, we'll give you the order. It's going to be NaNO3. So as I look at this chemical formula depicted as NaNO3, NaNO3 tells me that there is 1 sodium, right? Na, no subscript. If there was no sodium, it wouldn't be here. There must be some sodium. Since there's no subscript telling me it's 2 or more, it must only be 1. 1 sodium, 1 nitrogen. There's a subscript to the O, subscript of 3. Tells me I have 3 oxygens. So NaNO3 would be the chemical formula for that molecule. How many atoms are in the molecule? Here's another way of turning it around. Not asking how many of each, but altogether, how many atoms in total are in the molecule whose formula is Na2HPO4? How many building blocks? How many individual building blocks are in that molecule? Does everybody see that? Everybody see 8 of them? Because I've got 2 sodiums, 1 hydrogen, 1 phosphorus, and 4 oxygens. So Na2HPO4 has a total of 8 atoms. 8 individual pieces come together to build that structure. 8 individual atoms to form that molecule. Take a moment to get on page with you guys. Here. On Your Own 2.7 asks to give the formula for each of the following molecules. 1 potassium and 1 bromine. What would the chemical formula for that molecule look like? 1 potassium and 1 bromine. KBr. I have 1 potassium and 1 bromine. If I had no potassiums, the K wouldn't be there because K is a symbol for potassium. If I had more than 1 potassium, it would be subscripted with 2, 3, 4, whatever. 5 carbons, 10 hydrogens, and 5 oxygens. Mm-hmm. C5H10O5. It's not rocket science, is it? It's pretty straightforward once you see it. Beginning of class, you might have said, I have no idea. Now it's like, oh, that's easy. I've already seen 2 of them. There we go. Lithium sulfate, Li2SO4. 2 lithiums, 1 sulfur, 4 oxygens. How many molecules, or excuse me, how many atoms are in the molecule rubidium chloride, RbCl? 2 atoms. KMNO4.
6.
Yep, 8. 3 sodiums, 1 phosphorus, and 4 oxygens. HC2H3O2, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms to form that molecule. Now, we've already covered how to determine if an element is a metal or a nonmetal based upon where it sits on the table relative to the jagged stair-step line, right? We've got the stair-step that's over here. It starts at boron. The red line right here, it's in your representations in your book as well. If the element is to the left of that, it's a metal. If it's to the right, it's a nonmetal. We've already covered that. Molecules also have properties. Just as we've said metals and nonmetals, those are for the atoms, the individual elements. Now we're going to talk about the molecules. And they're going to be either an ionic molecule or a covalent molecule. Those are the two basic types of molecules, ionic or covalent. Ionic compounds conduct electricity when dissolved in water. You recognize that, right? That pure water does not conduct electricity. That if you were in pure H2O and there was nothing else in that container except molecules of H2O, that you could drop an electrical line in one end and a grounding line in the other one and you'd be fine. You can't. Water itself, H2O, does not conduct electricity. But yet you know that water, you tend to think water does conduct electricity, right? Used to be, you know, the old, you got the CFIs or CGI breakers now. The breakers that interrupt the circuit whenever, you know, it used to be that people would commit suicide by dropping a toaster oven into the bathtub and fry themselves to death, you know. Or people would try to murder someone by dropping a hairdryer in the shower or in the tub so that they would fry. Well, the reason that worked was because, first of all, they didn't have electrical circuits that would automatically shut off the circuit with that kind of current being pulled. But second, because water, we seldom, if ever, have water that is simply H2O. There's generally things that are dissolved into it. As a matter of fact, if you had the option of drinking pure H2O, you wouldn't like it. It's wet, but it has no taste. Water has no flavor. Now, there's a huge industry that takes water and puts things into it so that you like it, not to the extreme of Gatorade, but just to mineral water, flavored water, vitamin water, things like that. They put things into the water so that you actually like the water more and will tend to drink more water. But water itself, H2O, pure distilled water, is bland tasting. It's wet. It doesn't satisfy in terms of your sense of taste and appreciation. So they go through and they mix things into it. You know, Gatorade is the extreme, where they mix a lot of electrolytes in there, potassium and so on, mix it up in there so that you, and sugars and stuff, so that you like it. But tap water, as it comes out of the tap, is H2O plus a whole bunch of other minerals, ions that are dissolved into that. Gives it its flavor, but it also conducts electricity. It's those additives to the H2O that conduct electricity, not the H2O. Okay? So, but ionic compounds, they do conduct electricity. That's one of the characteristics of it. So a compound is an ionic compound if it conducts electricity when you dissolve it in water. If we have a beaker of water and we have a circuit that water is part of, we've got 2 electrodes in the water. Pure distilled water, the circuit wouldn't be completed, but as soon as we dump something into that water and stir it up that's ionic, suddenly electricity passes through that water and the circuit's complete and the light bulb comes on. Why does electricity flow? Because an ionic compound was dissolved in the water and that compound, now in solution, conducts electricity. So a compound is ionic if it conducts conducts electricity in water. If it has at least one metal atom in its formula, this is the key right here. This is not so much a characteristic as this is what's causing this to happen. All right? If there is at least one metal atom in its formula. So, for example, salt water. Let's say we had a circuit. Maybe you can't visualize this yet, but by having a circuit, I'll say that we've got a beaker that has water in it. And I have one electrode on one side and one electrode on the other side. From that electrode, I come up and I put a light bulb. And from that light bulb, then I go over and put a battery. Okay? I've got this circuit. If this is pure H2O, no electricity is going to be flowing. The light is not going to be lit. If I take some sodium chloride, NaCl, I put it in this water here and I mix it up, suddenly that light bulb comes on. Why? Because I've put a compound in here that is ionic, and when I stirred it up, the ions of the sodium and the chlorine now are passing electrical charge back and forth between these probes. I know that's going to happen because one of the characteristics / one of the reasons for that is that for sodium chloride, I've got sodium and chlorine. I have a nonmetal and a metal. And since I have at least one metal, that whole compound is going to be ionic. If it has at least one metal in its formula, it's ionic, and it's going to conduct. Acids are an exception. There's almost always an exception to things, but for right now, we're going to ignore acids. We'll get to that in the chapter on acids and bases. So for right now, if it's a metal, if it has at least one metal in the formula, it's ionic and it conducts. It's good for now. If it's not ionic, it's covalent. It only has non-metal elements in its formula. So compare and contrast sodium chloride. Said before, sodium chloride, NaCl. This is a metal and a non-metal. And therefore, actually the therefore symbol are these three dots. So therefore, it's ionic. If I have carbon dioxide, it's a nonmetal and two nonmetals, and therefore it's covalent. We are not going to have compounds that have two metals. We're not going to have sodium-potassium combination. Okay, they're both metals. We're not going to have any of those. The only thing we're going to have is either the molecule is going to have a metal in it or it's not. And if it has a metal in it, it's ionic. And if it doesn't have a metal in it, it's covalent. What the word ionic and covalent mean, we'll get into that a little bit later in the course. So there are exceptions. Those are polyatomic compounds. And again, we will get into those later. It's a special case. For right now, it either is covalent or ionic based upon if it has a metal in it, it's ionic. If it doesn't, it's covalent. Some examples. Table sugar. Let me erase this over here. Looking at table sugar. Table sugar is made up of 12 carbons, 22 hydrogens, and 11 oxygens, okay? So table sugar, C12H22O11. How many atoms are in sugar? How many atoms make up one molecule of table sugar? $45, right? 45, 22, 32, 34, 44, 20, 30, 44, 45, yep. So 45 individual atoms come together to form one molecule of table sugar. But if I were to take that and put it in a beaker with this circuit around it, I put sugar in here and stirred it up, the light would not light. It would not light, which means it must be covalent. Does that make sense? Let's look over here. What makes up this molecule? Carbons, hydrogens, and oxygens. That's all that's in it. Are any of those metals? Go over to our periodic table. Let's find them. Carbons, oxygens, and hydrogen. But remember, hydrogen is the exception. It's on the non-metal. It's on the metal side, but it is actually a non-metal. Okay? So carbons, hydrogens, and oxygens, these are all nonmetals. Since they're all nonmetals, it's covalent, and we would not expect it to conduct electricity. So if you had pure H2O and you stirred sugar into it, made sugar water out of that, you can't be shocked if you were in it, because no electricity would be transferred through the water. If you jumped into salt water, sodium chloride, or potassium chloride, because sodium and potassium are metals, it is ionic, and therefore you would be shocked. Baking soda. The formula for baking soda is NaHCO3. If you look at, obviously, we've got sodium at the very front end there. We've got at least a metal, sodium. So it's ionic, so it does conduct electricity. So classify the following compounds as ionic or covalent. SiF4. So what are we in search of? Search of metals. Basically, this is what it comes down to. In search of a metal. If we find one, it's ionic. If we don't, it's covalent. So we've got silicon and we've got fluorine. Silicon, for our purposes, it's to the right of the stair step. Fluorine, to the right of the stair step. So all the building blocks, all the atoms that make this up are to the non-metal side of this jagged line. So they're all nonmetals. So therefore the compound must be covalent. They're all nonmetals, and therefore it's a covalent compound. Calcium bromide. It's ionic because calcium is a metal. Ooh, it's too long, it's too hard, I can't do it. No. Same principle. Right. Since lithium is a metal, it's ionic. You're just looking for one. So if you start from the beginning, go lithium, metal, done. It's ionic. How do you know? It's got a metal in it. But what about the rest of it? Doesn't matter. It's got one. It's ionic. Covalent. Has to be. Again, it's another carbon, hydrogen, oxygen chain. CHO. I'll just say, I'll start, later on in the course, I'll just start saying it's a CHO chain. CHO. CHOs. It's some combination of carbons, hydrogen, and oxygen. So they're all nonmetals. It's a covalent compound. The thing about naming these compounds is that every ionic compound includes both metals and nonmetals in its formula, its recipe, right? When it's ionic, the name comes from taking the metal, and then taking the nonmetal. So in this case, sodium chloride. You never hear it referred to as something like, and it sounds so weird to our ears, we can't even sometimes make it up. It's not chlorosodiumide, right? It's sodium chloride. It's ionic. How do we name this? Well, we take the two elements that make it up, sodium and chlorine. We take the name of the metal and just write it directly. Sodium, sodium. Okay? Chlorine, we change the tail end of it slightly. We give it its "-ide" ending, known as the "-ide" ending. So we take the metal, keep it. The nonmetal, we "-ide" it. Sodium chloride. If you look in your book on table 2.1 on page 67, it gives you the common "-ide" endings for nonmetals. See hydride, carbide, nitride, oxide, fluoride, phosphide, sulfide, chloride, bromide, and iodide. Notice the line above where it says table 2.1. It says you need to memorize table 2.1 for the test. So you look at that and say it's a sodium, it's a chlorine, so it's a metal, non-metal, it's sodium and chlorine with its ide name. What is its ide name? Sodium chloride from the table. One sodium, one chlorine. The ones are implied, so it's NaCl. Never form any other kinds of combinations. That's the thing about ionic combinations. If you know the formula for the ion, or excuse me, if you know the name for the molecule, in this case sodium chloride, sodium and chlorine only combine 1 to 1. You're never going to have Na2Cl or NaCl2. Once you know how they combine ionically, that is the only formula, the only way that they're ever going to combine. So if you put sodium and chlorine together and you react them, there's no mystery on what you're going to get, right? You're going to get sodium chloride. You're going to get Na1Cl1, or just written NaCl. That's the only way they combine ionically. So the first element is the chemical formula is the metal. The metal always leads in the name of an ionic compound. So if it has potassium in it, it's going to be potassium something. If it has lithium in it, it's going to be lithium something. Sodium, sodium something. Beryllium, magnesium, calcium, it's always going to start with that name. The metal always comes first. The nonmetal trails and gets its ide name. The table from your book. So we start with the metal, replace the last element with the ide name, and then just read them in order left to right. We already did sodium chloride. So sodium and chlorine become sodium chloride. It's just walking through the same thing. How about this one? K2O. What is K? Memorize that. It's potassium, right? K is potassium. So this formula tells me that 2 potassiums are combining with 1 oxygen. Potassium is a metal, oxygen is a nonmetal, it's ionic. Which means when potassium and oxygen combine, they're always going to combine 2 to 1. It's always going to be K2O. I'm not going to have K3O or K2O2 or KO2. It's always going to be K2O. What's its name? Start with the metal. Potassium. The nonmetal is oxygen. It gets its ide name, oxide. So K2O is potassium oxide.